All right, I guess we can start. So, hi everyone, finally. So welcome to DuQIS very first quantum computing workshop. I'm very excited about this event. I hope you're also excited about learning these cool stuff. So my name is Nora, and I'm a junior studying math and computer science. So today you'll mostly hear me and Edwin talking. So Edwin, you want to introduce yourself?
Hello, I am Edwin. I'm also a junior, also studying computer science, and also a member of DuQIS.
Yeah, so thank you. So what we want to do today is to introduce you the most general ideas in quantum computing without any technical details like equations, derivations, theorems, just to scare you away, no. And another purpose, as you may have heard, so Duke is having a quantum supremacy talk by a researcher from Google, Dr. Jimmy Chin, next Friday. So he will start from the introduction, but later on builds up to quantum supremacy and Google's quantum supremacy experiment. So our workshop today is to set you up if you don't know anything about quantum, and also just to show you how interesting this is. So we can just start our workshop official part today. A quantum computer, it's still a computer. So it does the same computation for you, and it also processes information. The only difference is that all these tasks are accomplished using quantum mechanical systems. And quantum mechanical systems are completely different from the classical system that we're using right now. So in terms of an operational point of view, they're different in, for example, how they store information or how calculations are done. So in a conceptual way, they just explain the world differently because they follow two sets of physical rules. So quantum mechanics is nothing fancy. It is a mathematical framework that or set of rules for the construction of physical science. So it is able to explain things that couldn't be explained by classical mechanics when the objects get really small, like atoms, molecules, or ions. And we can say that quantum mechanics is a better interpreter for the real world. In addition to that, it also inspires us. Maybe we can think physically about computation. So what does it mean, like think physically about computation? Since our world is constructed by atoms, molecules, ions, electrons, maybe we can just simulate their behaviors of the world on a quantum computer, because quantum computers follow the rules of quantum mechanics, and atoms, molecules, ions also follow the rules of quantum mechanics. So this just leads to quantum simulation. And this is a great illustration from IBM research. At the bottom left, it shows the most complex molecule that we can simulate on our world's most powerful supercomputer, and it is F cluster. So as you can see, the molecule is not complex at all and not very complex at all. And if we want to model more complex molecules to discover better drug treatments or understand our biology better, then we'll need a different approach, because even for very simple molecules, the number of quantum states in a system can be enormous. So if you don't understand the term quantum states, it's okay, because we'll explain it later. For now, you just need to know that it requires tons of classical computations on a classical computer, so it couldn't afford it. And we'll show you some stats here. So a laptop can model a 26 electron system, and a supercomputer can model a 43 electron system. And in principle, a quantum computer with 300 qubits, and qubit is something that is analog to the classical bit and 0 and 1. And we'll talk more about that later. So a quantum computer with 300 qubits could perform more calculations in an instant than there are in the universe. And this is all because quantum computer can keep up with the true complexity of nature. So we just talked about quantum simulation, and I'll have Edwin introducing you some other interesting things that quantum computer can do that a classical computer couldn't.
Thank you. So, as Nora was saying, quantum computers are very good at simulating quantum systems, but there's also many other things they can do. One of these is searching. So imagine you had some list of elements and you wanted to find the particular one, which in this picture is purple. On a classical computer, the best way to do that is to go through them one by one and check if it's purple, and if it is, then you stop. So in the worst case, if this purple one was at the very end, this would take n steps. On a quantum computer, however, you can actually do this in a square root of n steps, which sounds crazy, and it is, because the way it does it is by quite literally looking at every single element in the list at once, and then performing a couple of steps which make sure that you get the right one at the very end. And so you can see that it's kind of relying on a completely different approach to the classical computer. Now, search is a very, very important problem. Any problem in computer science can be modeled as search. In particular, if you're looking to, for some examples might be looking to optimize some variables, or planning or playing a game, say in tic-tac-toe, you might think you search ahead at the various moves and then you pick the best one. So we will now move on to factoring. Classically, it is very hard to factor numbers. So if I was to give you 15 and you would, the computer would have to give back 3 and 5. Pretty much the best way that a computer would do this classically is they'll take a guess and then they'll check if that number divides. So while that may work for a small number like 15, if it's instead got 100 digits long, it's going to take a lot of guessing and a lot of checking to see if those numbers can be factored. Quantumly, however, we have Shor's algorithm, which can factor numbers exponentially faster than a classical computer, and therefore they can do it efficiently. This may just sound like a slightly impressive but rather boring mathematical trick, but it's actually very important. Public key cryptography relies on the difficulty of factoring large numbers, and that's what secures your payments on the internet and keeps your passwords safe and everything like that. So the basic idea is two people will choose two random prime numbers, say X and Y. X will be used to make what's called the private key, which you keep yourself, and then X times Y will be used to make the public key, which being public means you can publish it anywhere. And because it's so hard to factor X times Y back down to X, it's assumed that no one's ever going to guess your private key. And so your transactions are safe, your passwords are safe, and everything like that. The encryption that's used on the internet, which is called RSA, typically uses 1024 or 2048-bit keys. And as this article shows in the corner, there's predictions that quantum computer could break that in 8 hours. This isn't possible yet, is an important caveat, but as these computers continue to get bigger, they will very soon be able to break encryption. And that's why people are already getting ready for it, and they're developing what's called post-quantum cryptography, which rather than relying on something like a kind of mathematical assumption about difficulty of factoring, it's trying to rely on the laws of physics to be more secure. So you're also probably wondering, how does any of this work? An important experiment at the beginning of quantum mechanics is something called the double slit experiment. And this is where they kind of started realizing how weird all of this stuff was. So the basic idea is you've got this electron gun on the left, and you shoot electrons through a screen which has two little slits, which are some distance apart. And then the idea is the electrons go through the slit, go through the slits, and then are collected on the screen at the back. And it will light up when an electron lands there. So if you were to think of an electron like a tennis ball or a particle, you would expect that, it goes through one of the slits, and then you get a roughly kind of Gaussian shape on the end, where it's more likely in the middle and less likely at the edges. But instead, there was this thing called an interference pattern, which is shown a bit better in this bottom picture, where there's parts even in the middle where no electrons ever land, and then there's parts where they land with a lot higher frequency. And what that indicates is what's called the wave the wave particle duality of electrons, which basically means it's able to interfere with itself. And so they thought, oh, maybe it's just because we're firing lots of electrons through at the same time. They're bouncing off different ones, and then that's giving this pattern at the end. So they slowed the gun down, they fired one at a time. And they found that you still get this pattern on the screen. And so the only explanation for that is that a single electron is going through both slits at the same time, bouncing off itself, and then hitting the screen at the end where it's detected. And that's very important to keep in mind. This idea of being able to go through, or to be in literally two places at once. This is where we begin to see some of the advantages. Another weird feature was when they tried to place a detector on one of the slits, this interference pattern went away, and it instead gave you very classical, or I say boring behavior, where it seemed like it only went through one slit. So not only can it be in two places at once, but it also seems to have some weird relationship to being measured as well. And we'll talk a bit more about that later. So how does this work? On a classical computer like the ones we're all on now, everything is made out of bits. A bit can be 1 or 0, which can be thought of as a switch being on or off. These are built using transistors. Quantumly, however, you have a quantum bit, also known as a qubit, and that can be 0, it can be 1, or it can be both quite literally at the same time. So from our previous example, it could be both in the top slit and the bottom slit at the same time. This could be represented using anything which behaves according to quantum mechanics. So this is going to be small things like electrons or photons or atoms. In the classical world, transistors weren't the first things that people made computers out of. There was a lot of competing different approaches, like vacuum tubes and stuff like that. That's kind of the point that quantum computing is at the moment. No one really knows the best way to build them. So what else is going on? So we write a 0 state using this line and the angle bracket, which is known as a ket. And that corresponds to a vector. So you can see that the 0 ket is the 1, 0 vector. And if you want, you can imagine that like a switch where the 1 is the up. And so the 1 state is the vector 0, 1, where the switch is down. The reason this is important is because we can make use of something called superposition, i.e. being in two places at once, to mean that it is both the 0 in the 0 state and the 1 state at the same time. And we use these Greek letters, so we would normally call it psi, and it's equal to alpha times the 0 state plus beta times the 1 state, which is basically just this vector here at the end of alpha and beta. And then this little sphere at the bottom is called the block sphere. And the general idea is that a qubit can be any point on the surface of that sphere. But you're probably wondering, what does a superposition actually look like? And why have I never seen one? And for that, we need to talk about measurement. So when you measure a superposition, it collapses to 0 or 1 probabilistically. So you can only get one result at the end of the day. The probability of measuring the 0 is equal to the amplitude of alpha squared. And the probability of measuring 1 is equal to the amplitude of beta squared. And so if you know your probability, you'll know that these have to add to 1. But you'll also realize that it means that alpha and beta could take negative or even complex values, which means that they can take a whole, rather than just saying, oh yeah, there's a 50% probability of being 0 and a 50% probability of being 1, you could say there's a minus I probability of being A. Sorry, but that wouldn't be a probability, but there's a minus I, what's called amplitude. in the 0 direction, let's say. And so it's as if there's a lot more space available just for a single qubit to occupy compared to if we were thinking about the classical bits. So measurement does destroy the superposition, and unfortunately it's irreversible. And sometimes the environment will accidentally measure a qubit. Let's say if you get too close with it, it thinks you're trying to measure it, and so it will collapse. And this is known as decoherence. There's also a problem of what truly counts as a measurement. This is known as the measurement problem, and it's kind of famously encapsulated in the Schrodinger's cat experiment, where we have a cat in a sealed box, and there's a vial of poison which is rigged up to a quantum process. And so the idea is if the quantum process has kind of both happened and not happened literally at the same time, i.e. it's in a superposition, then the cat must be both dead and alive at the same time. This was meant to show that measurement is very strange and makes no sense. But it kind of also indicates some of the confusing parts about quantum mechanics. I see what a question. Yes, you're right. So while alpha and beta are complex and maybe negative, since we're squaring them, that's how they always come back to being real and non-negative.
You can imagine them as taking their mode of it. Is that like length, like the real part squared plus minus the complex part squared.
Yes.
Square of that. Yeah.
Yeah. Thank you for the question. So the idea is that right up until it's measured, it has these complex values, and then once we measure it, we take the absolute value and we square it, and then it becomes slightly more comprehensible. Okay.
I think it's a pretty good point before we proceed to quantum circuits and entanglement. Does anyone have any question about what we just talked about? Modular squared of alpha and beta. Or is there any place that is probably unclear and you want us to kind of repeat? Because when we get to entanglement, it is kind of built on superposition. Everyone's cool?
All right.
Okay. Yeah.
That's good to know. We'll keep going.
Yeah.
So in a classical computer, there is only one thing you can do to a classical bit, which is flip it. I mean, well, technically you could do nothing to it, but I wouldn't count that. So the only thing you could do is to flip it. Hold on, I see we have a question. How do we know a superposition is real if we can't measure it? That's a very good question. And that is kind of what the double slit experiment that I showed earlier proves, because we can see that before they hit the screen, a single electron is bouncing off itself. And so to bounce off itself, it has to have gone both through the left slit and the right slit at the same time. And therefore, you know, it was in a superposition, even though as you point out, we could never actually directly see that superposition.
And it's not technically that we cannot measure it, we can always measure it, but our measurement will force a state that is in between 0 and 1 to choose a side. We'll force it to choose whether it wants to be measured at 0 or wants to be measured at 1. So that's where the probability parts comes in. So like a pretty typical way of verifying the existence of superposition is to just have the same qubit and then not have the same qubit, but like repeat the measuring experiment and to see like the probability of landing in a 0 and landing as a 1, whether it is the same with something that we predict it to be. Does that answer your question? Yep. Okay.
So yeah, the one thing you can do to a classical bit is flip it. So you can turn it from a 0 to a 1 or a 1 back to a 0. You're probably going to guess, but on a quantum computer, there is a much bigger range of things you can do to a qubit. And these are all represented as reflections or rotations on the block sphere, which is these spheres at the bottom. If you remember that the states are vectors, this means that it's useful to represent all of these operations as matrices. So you can see this is where the linear algebra comes in. But we're not going to go into too much detail about that. The main thing to remember is that all of these operations have to be reversible. And so some of the important 1-qubit gates are shown at the bottom here. We have the Pauli X gate, or just the X gate, which takes the 0 at the top to the 1 at the bottom, and it takes the 1 at the bottom back up to the 0 at the top. And so this is a reflection around the x-axis, hence its name. The Y gate takes 0 to I1 and 1 to minus I0. And finally, the Z gate, or the Z gate, as you Americans would say, takes 0 to 0, and it takes 1 to minus 1. And notice that if you were to apply any of these twice, it'd be the same as doing nothing. And so we can see that they are very easily reversible. So moving on to the Hadamard gate, which is far more interesting. This one is the one that can create a superposition. So looking on our block sphere, it's this blue arrow, which takes it from 0 to 0 plus 1 over root 2. Remember, it's root 2 because we're saying there's a 50% probability of measuring 0 and a 50% probability of measuring 1. And we get that by squaring 1 over root 2. This is kind of written in shorthand as the plus state. But also, if you prefer, we have the vectors. It's 1 over root 2 and 1 over root 2. And similarly, the Hadamard gate will take the 1 state to the minus state, which is similar, but with the minus sign, as you can guess. And so this will also measure 0 and 1 with 50% probability each, but clearly has some differences as well due to that minus sign. And once again, this gate is reversible, and it's actually its own inverse. So applying H back to the plus state will take it back to the 0, and applying H to the minus state will take it back to 1. Are there any questions about any of that?
Move on.
All right. So we've only talked about 1 qubit so far. What happens when you start to want to have more than one, which is probably when it gets useful? Mathematically, they are combined using this thing called the tensor product, which basically just stacks up vectors, but is more conveniently written in this ket notation as just 0, 0. Or 0 tensor 1 would just equal 0, 1 in a ket. So there's 4 different things that 2 qubits could end up in, which as you might have guessed would be 0, 0, 0, 1, 1, 0, and 1, 1. And because of our superpositions, it can also be in all 4 of them at once. So if we do the Hadamard gate, that's what the H is, on each qubit, so that's why it's tensor 2, because we're doing it on both of the zeros, then we end up in 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 over 2. And that means that there's a quarter probability of measuring each of them, because once again, we square the half to get a quarter. Notice that with 1 qubit, we had 2 possible states, 0 or 1. With 2 qubits, we've now got 4. This is going to scale exponentially. In other words, these vectors will become exponentially long. And so this means that for every extra qubit, it would be doubly as hard to simulate it on a classical computer, because you have to keep track of all of the different components in the vector at once, whereas using a quantum computer, it's stored like physically in that qubit. And so by the time you get to 50 qubits, that's 2 to the 50 different possible states. That's already a ridiculous amount of memory that you've got to use up if you were to do it on a classical computer. All right, so there's an important 2-qubit gate, which is called the C0 gate. And for any computer scientists, this is basically the same as the XOR gate. It has a control and a target, and the control is this top one with the black circle, and the target is this white one with the cross. And what it does is, if the control is 1, it will flip the target, and otherwise it will do nothing. So you can check this kind of truth table here. It does nothing to 0, 0, but it will flip the second qubit in 1, 0 to go to 1, 1, and so on. This is all fine, but if we're thinking quantum mechanically, we've got to ask, what happens when the control is both? What happens when the control is in a superposition? Does it flip the target? Does it not flip the target? Doesn't make any sense. So the answer is, we got to use the linear algebra that God has given us. So if we look at this diagram on the right, we see that there's the 2 qubits. They both start in the 0 state. We apply a Hadamard to the top one, and that gives us psi 1, which is 0, 0 plus 1, 0 over the square root of 2. And then when we apply the C0 gate, all we have to do is expand the brackets. Or in other words, if we're saying the control is both 0 and 1, we have to treat the target when the control is 0 and when the control is 1. So we have to do both at the same time. And it has to correspond to the one that it's thinking. So you could imagine it has split the qubit, and now it will follow both paths. So it will apply a CX to the 0, 0 part, which is to do nothing to it. And it will apply a C0 to the 1, 0 part, which means it will flip the second qubit. This means that our final state is 0, 0 plus 1, 1 over root 2, which doesn't look very interesting, I know, but it's in fact very, very crazy. For one reason is that if you were to imagine, after performing these 2 gates, you then separated the 2 qubits. Typically we say one goes to Alice and one goes to Bob. So imagine Alice flies to the other end of the universe and Bob stays on Earth. At this point, it's still in the state 0, 0 plus 1, 1 over root 2. But the second that Alice measures her qubit, remember there's a 50% probability she'll get 0 and a 50% probability she'll get 1. Let's say she gets 0. As soon as she gets that, she will know with absolute certainty that Bob is going to get the same thing. She doesn't have to ring Bob up and say, hey, I got a 0. Like, what did you get? She will know. And indeed, this has been tested. These measurement results are perfectly correlated, which is absolutely not possible classically. And this has raised many eyebrows, but is also one of the most powerful features of a quantum computer. Shor's algorithm, which we looked at beforehand for factoring, exploits entanglement. Pretty much any quantum algorithm is going to need to use entanglement in there somewhere. But if we go on to the next slide, we'll see that Einstein was not happy about this at all. He described it as spooky actions at a distance. Because if you've got one measurement instantaneously affecting the other, no matter how far apart they are, this seems to break the assumption of locality. No one really knows whether or not it breaks locality. It does actually seem quite likely. It's a very big debate continuing in the quantum physics community. Einstein thought instead that the state before being measured still already knew what it was going to be. And it was as if before the two qubits were separated, they had kind of already secretly agreed they would be measured to a 0. That has been empirically disproven. And so that means many people just say, all right, then we have to give up on locality. We're not going to worry too much about that, but just a little interesting tangent. But the main idea here is that entanglement can allow very, very close interactions between two qubits. And it's almost as if doing one thing to one will be reflected onto the other. And so one application of this is in quantum teleportation. It's quite a simple circuit. It's just this thing on the left. Not going to go through all of it, but notice the first two gates. We have the Hadamard and the C0. So we're going to create these entangled qubits. A stands for Alice and B stands for Bob. So all that happens here is Alice and Bob share an entangled pair of qubits. And then Alice also has her qubit at the top called psi. Once they've made their entangled pair, Bob can then fly off to Mars or whatever. Alice applies a couple more operations to her qubits. She then unfortunately has to measure them and ring up Bob and tell him what she measured. Bob then applies the appropriate correction, and the state psi has quite literally been teleported from Alice to Bob. Remember that without this, there would be no way you could ever send someone a state, because if it was in a superposition and you measured it to try and get an idea of where it was, you've only got one measurement you can make. And so you can never actually know what it was beforehand. But the workaround is you can instead literally teleport your state to the other person. And this has been done in the real world. Some researchers in China, as this article is describing, sent a photon into space using teleportation, which I think is very cool. And people also have hopes of using teleportation to create a quantum internet.
Do you have a question, or you want to wrap it up first?
So there's a question about teleportation. So I may as well answer that. So it says, does this work? This works over planetary distances, but does it work over infinitely large? In theory, yes. And that's what's kind of crazy about it. So there's two caveats. One is, remember earlier I talked about decoherence. There's the danger that let's say the box that Bob is carrying his qubit in accidentally measures it without him knowing, and then destroys both his and Alice's qubit. That is, that's more likely to happen over longer amounts of time. And so just in the process of Bob flying through space, it might break it. The second caveat is that it does need these on the diagram, these are these double lines, which are the correction. And that's the classical communication. So that's where you have to ring them up and tell them, Alice has to say what her two measurements were. And so that is going to happen at less than the speed of light, and so does apply a restriction to how far it could be. But the quantum channel, as it's known, isn't affected whatsoever by distance. It's just the kind of afterthought that does add a limit. There's a question to reiterate what is meant by a measurement. A measurement is like in normal computer science, it would be like print X. But in quantum computing, it's as Catherine has said, it's the projection into the eigenspace, which is getting a bit mathematical, but basically it is when it goes from the superposition to one of the definite values, i.e. 0 or 1 for each of the qubits. and this happens by applying a physical measurement to it.
I also tried to give an explanation on measurement. So we just said that we have a block sphere that is a sphere. So a vector that is pointing on a point in the sphere is a vector and is also a quantum state. So we said that this is 0 and this is 1. So but these are the base state. Like speaking of a linear algebra kind of language, the base 0 and 1, they are orthonormal bases that constitute the basis for this space, that is the sphere. So any vector that is pointing something is constituted by this 0 and 1. So when we're measuring it, because we wanted to force it to be whether 0 or 1, so we are kind of making this vector to choose a side. So this is called measurement. Because yeah, quantum state, it's kind of abstract, something abstract, and we want to make it concrete by forcing it to pick a side.
Yeah, another way to think of it is that superpositions might be able to exist on the quantum level with electrons going through slits or photons or whatever. But if you assume that we could never see a superposition, if you assume that classical mechanics applies for big things, then we know when it gets big enough, it has to be one or the other. And so this is quite controversial. There's many different interpretations of quantum mechanics, but some of them, in some of them, the general idea is once the effects of a superposition are magnified to like the observable level, it has to be 0, 1, it has to be one or the other. But yeah, the measurement it's a big problem in understanding it. Like no one really knows how it works, and it seems strange to assume that it has to instantaneously collapse. But yeah, there's just one more recap slide, I think, here. So some of the pros of quantum computing that we've described is it can be in a superposition, can be both 0 and 1 at the same time, and multiple qubits can be entangled. So they can share information at very unexpected levels. Also, I think a pro is that it's a very young field and no one really knows, it's not all been completely worked out yet. So there's a lot more discoveries still to come. But there are also some cons, which is that measurement will destroy a state, and they are very fragile, and sometimes they are accidentally measured. You're also not allowed to copy a state. You can teleport it, as we've seen, but you can't share it in the same way. And finally, every operation has to be reversible, which is just something to keep in mind when you're imagining how to build a circuit, because this means that you can't do something like a for loop in classical computer science. Those aren't allowed because they overwrite information. But yeah, before I hand back over to Nora, are there any other questions?
People can open their Mac and just say things.
Otherwise, I'll pass back to Nora. Thank you.
Yeah, because that's the end of our most technical parts. Okay, cool. So, the number of qubits of a quantum computer, it's a really important metric on its computational power, because naturally, the more qubit it has, the more powerful it is. So let's take a look at this graph of the 20 years development of the quantum computing industry. So in 1998, we start with 2 qubit. 2 qubit system or 2 qubit device, 2 qubit quantum computer, divided by invented or developed by IBM, Oxford, Berkeley, Stanford, MIT. And then it gradually grows to 48 qubits, 2018 by Intel. And also Google, the quantum supremacy Google declared also happened on their 53 qubit quantum device. And they also declared 72 qubits device the same year. And Rigetti said that they're gonna have a 128 qubit device by the end of 2019. But like when I was trying to find the news of that, I didn't find it. So maybe they didn't actually realize their goal. And actually today, like this month, IBM announced a roadmap for its development of its quantum computer, saying that they will have a 1,000 qubit quantum computer by 2023. Well, currently its largest quantum computer, which is revealed this month, contains 65 qubits. And their ambitious goal includes building an intermediate size of 123 qubit and in 2021 and 433 qubits in 2023. But on the other hand, it is far from enough to only have 1,000 qubits when your qubits are not stable at all, which means the error rate is going to be super high. Developers want qubits that are reliable as a bit in an ordinary computer. So most of the quantum algorithms require the qubit to maintain its state as long as possible to make the calculation right. But however, real qubits are far less stable. So we can just take the superconducting qubits that IBM and Google use as an example. So this is a device that consists of 4 superconducting qubits. You can see in the middle, fabricated and published by IBM in 2017. So Google IBM Rigetti uses this qubit make of tiny resonating circuits of superconducting metal and put them into microchips, which so far have proved easier to control and integrate into circuit than other type of qubits. So in this kind of type of qubit, each circuit has 2 distinct energy states, which can denote as 0 or 1. So by playing a circuit with microwaves, researchers can ease it into either state or any combination of the two. Let's say 30% of 0 and 70% of 1. But those in-between states can easily fuzz out or like decohere in a fraction of a second. And even before that happens, noise can jeopardize the state or alter it, so potentially derailing a calculation. So in summary, what does it take to create a fault-tolerant quantum system? And what does it take to increase the computational power of a quantum computer? There's some questions. Okay. Yeah, so one is to increase the qubit count. As we just said, the more qubit you have, the more states the quantum device can manipulate and store. And the other is to have low error rates, which are needed to manipulate the qubit state accurately and perform sequential operations that provides answers but not noise. So sometimes if you may end up with 90% of noise and 10% of like real things, the accurate thing you want to know about in the end, after a sequential of operations, if you don't have some control over the errors. So this way we can define a metric called quantum volume to understand the quantum capacity. And it measures the relationship between number and quality of qubits, circuits, connectivity, and error rates of operations. And our goal should be to develop systems with larger quantum volume, which means larger number of qubits and low error rate. So you can see that even if we increase the qubit number, it doesn't improve the quantum volume because the error rate is super high. And when we have the same number of qubits, we just decrease the error rate, and we'll have a boost over the quantum volume. So, so in this race of building a quantum computer or building a powerful quantum computer, like lots of companies are pursuing many types of quantum bits. Each type has its own strengths and weaknesses. But today we'll only have a look at 2 of them because the first one is the most popular one, and the second one is what DuQIS is using. So it's called trapped ion. This company that use trapped ion called IonQ is co-founded by 2 Duke professors, Professor Johnson Kim and Professor Chris Moore from Duke's engineering school. And I believe they're also the CTO of the company right now. So the pros of superconducting qubits, if they're fast working and they build on existing superconductor industry, the concept they collapse easily and must be kept cold. And the pros of trapped ion technology is they're very stable and they have the highest achieved gate fidelity. And the concept, they have slow operation and requires many lasers to be operated on. So we just talked about the idea of quantum value, which depends on qubit count and error rate. So one way to lower the error rate is by error correction. So classically, if you have never heard about the idea of quantum correction, error correction, well, I'll explain it to you right now. So classically, bits are represented by 0 and 1. So when we're transmitting messages, we're sending 0 and 1, sequence of 0 and 1. But there are chances that in the long transmission, some bit will be flipped. So in this binary symmetric channel, this 0 bit can be flipped into 1 with probability p, and this 1 bit can be flipped into a 0 also with probability p, and with the remaining probability they'll stay the same. So for example, if we want to send this sequence in the first line, 1 0 0 1 1 blah blah, the sender wants to send this message, but when it gets to the receiver, he or she will get a message that is wrong because some zeros are flipped into 1 and some 1s are flipped into 0. So in this way, he or she will need a method to kind of first detect the error, and then second, they change their error back to make it right. So the most easier way, classically and very intuitively, to do this error correction is to have a mapping strategy, which is to, like this, we map 0 to 0 0 0, and we map 1 to 1 1 1. So in this way, we can encode a message like 1 0 0 1 1 into this really long stuff over here. So when we're sending it, even if we have something that is flipped, we can easily find it out. Like the 1 1 1 is received as 1 1 0. So we can know that with a really high probability, this message should be 1 1 1. So we can change it back to the correct version of the message. So this way we can have a correct message and decode it back into the original message. But as you can also see, this kind of encoding way has a really low rate because originally you only need to send 5 bits, but now you have to send 15 bits. So there are a lot of wise way of doing classical error correction, but in terms of quantum, things are different. So a lot of the, most of the classical strategy that we use to correct errors wouldn't be valid in the quantum scenario. So these two spheres displays the errors, quantum error that we can have. So as we just said, qubit is a state in the sphere. So doing a quantum operation is to rotate or reflect the vector around the sphere. So when I wanted to land somewhere like here, we want to make the vector land here, it got flipped. It flipped over these plane and got into this place. And for a phase flip error, it kind of rotate around the x-axis. So this kind of errors are something that quantum system would have. And why this is different is because first, we have the non-cloning theorem saying that we couldn't copy a unknown state. Oh, this is a question. How would one approach programming a quantum computer when it doesn't measure state until the end? Like, how does the hardware know how to manipulate memory according to the program without knowing what's in it? I would say, first of all, we are able to design the circuits. So even classically, you don't need to check when you have a well-developed unit. You don't have to check in the middle of that. So I believe the quantum system also want to have algorithms that work this way. But during this work, we're trying to make it fault tolerant because we can easily have quantum error that accumulate in the end to have some disaster effect. That's the difficulty, yeah. so my point is, that's like a working unit for classical system and also for quantum system. Does it answer your question, or did I misunderstand anything, Alex? Okay, so I'll continue the non-cloning part. So why the quantum error correction is different from the classical error correction? Non-cloning theorem says that we couldn't copy an unknown state. So we can only copy it when we know the state is. So in this way, really naturally, we couldn't do the mapping strategy that we just had, like map a 0 to a 0, 0, 0, and map a 1 to 1, 1, 1. We just couldn't do that. And on the other hand, as is said in the slide, measurement will be destroyed. Measurement will destroy the quantum state. So when we want to detect the error, like detect it in a classical meaning, we just couldn't do it. So it requires some specifically designed quantum error correction strategy to make it work. And I believe it involves some like entanglement knowledge, and we're not going to go on into details about it today. But just to let you know that error correction is a really important part in a quantum system, because that can easily happen anywhere in the system. So, and a lot of researchers are really active in the field. So just FYI. So as a conclusion or summary of today's workshop, as I said in the very first beginning, a quantum computer is still a computer. It requires all the components that a classical computer requires, like the hardware, your storage, your processing unit, and the quantum computer architecture, and the software part like algorithms, error correction, quantum compiler. If it came to our last talk given by Dr. Mark Jackson from Cambridge Quantum Computing. And this quantum computer technology, or say this kind of empire, has the potential to be as large as the classical classical computer industry today, or maybe it will exceed it someday. So we'll wait and see. And if you want to learn more, you can come to our next Friday's talk by Dr. Jimmy Chen, sorry, on quantum supremacy, beating a classical supercomputer using a quantum computing processing unit. And the Zoom link it's the same Zoom link actually, and you can find it in the newsletter and also on our Facebook page. And the second thing is we have a house course next semester. It's the first section for House 59. It's called Applied Introduction to Quantum Computing. That happens Tuesday, 7 p.m. to 8:30 p.m. We're gonna focus more on the applied side, and it's below 100 levels, so it's a pass and fail half credit course, and welcome everyone to register for it. And it has a limit of 15 people, but I believe you can audit it or just to let us know if you're interested. There's not really any limit for that, I think. Not question. Yeah, does anyone have any questions or general questions about anything? Well, our answer is we know it. Oh, the house course capacity is 18 people. But I think we can ignore the capacity, right, Catherine? Can we? Yeah, we can definitely negotiate.
There's been some really good questions in the chat. If anyone else has anything else to clear up, can ask away.
And thank you guys for staying, because we get a time confusion, and it also got me because I thought it was 8, and then like some other members of DuQIS like thought it was 8:30. So yeah, thanks for staying.
Yeah, it seems like there's been some questions about like how do you do something to a qubit without measuring it. And though that's kind of like, that's just how I see the central tension of quantum computing, because like you want to be able to change it, to do something with it, but if you change it too hard, it will collapse. And that's why there's so many errors, and that's why it's taken a while to kick off. I think I have an analogy is like you can, it's like you can do all of these magic things in this magic box as long as you don't look at it. So you have to like do it just with your hands, with your eyes averted. And so you've got to trust that your circuit is going to do the right thing. And yeah, of course, debugging is going to be very different. You can't just print X every 10 lines, because that will destroy all of the information in your circuit.
Another thing I want to add about this, because I think it's a really good point. Measurement is actually a way to give you classical information. So when you have a lot of unknown quantum information, the only way to get a classical information is by measurement. So when we say that measurement can destroy a state, we're saying it as a con, but sometimes it can also be a pros, because classical information is also a resource. So if you use this resource well, you can also do some amazing job by the measurement. And for a system, and another thing, in addition to that, for a system, the measurement, the thing that comes out from the measurement is our ultimate product of this algorithm or anything. In the end, we still want a classical answer to some problems, like the factoring. We want an answer about this prime factor, or whether it could be factored into two primes. Yeah, things like that. And the searching, we want to find the object in the end. So that's a classical version of the answer, and measurement can provide it to us. Yeah, just some random talk. Duke has some really good faculty, like good research faculty that is at Duke, because Duke has a quantum resource, quantum center, Duke Quantum Center. But all the courses are above 400 level, I believe, 500 graduate classes. And I think our house course is the first time that Duke is trying, like, we have faculty helping us, and the first time Duke is trying to put it in front of undergraduate student, and this half credit and pass fail. So it would be a really good opportunity for anyone who's interested in but afraid of trying it at a graduate classes to try it out here at the house course. So if you don't like it, we'll try our best to make you like it. And if you don't like it, you can just don't drop it and don't go to the graduate classes. That is hard. If we want, there's a question, if we want to take the house course but can't do it this semester, will be offered next fall. We haven't talked about it yet because so far it's only spring in front of us, but my personal wish is if we could reflect on our performance in the spring and then make a better version of it in the fall. I wanted to continue even after I graduate. Yeah. How does anyone want to share their thoughts about our workshop today? Just direct feedback to us.
Well, I just want to say that thank you everyone for showing up, and for the question about how do undergraduates get involved with quantum research. I think it's great that you're here because DuQIS, we started this organization because we want to make it more accessible to undergraduate students. We want to provide you guidance and resources, opportunities, share you all of that happens here at Duke, because we do have a Duke Quantum Computing Center here, and most people don't know about it. So we want, if you're interested in doing research, definitely show up more to our events. And also, I would say it would be good to just email like either one of us, like Edwin, Nora, or me, or just to reach out to us, or and we'll definitely give you more information and advice on what to do there. But there's definitely lots of resources at Duke. So
yeah, doing research about quantum is super cool, like from like how I experience it. But it also will be a plus if you know things about quantum before you started. I know it's hard because all the classes that it's offering so far are graduate classes, so you need to take you have to have some foundation before you start it. But you can learn with us or like self-study. I actually self-studied a lot before I do the research. That will equip you with some familiarity.
Yeah, there's some really good online resources, like videos and then like textbooks. That we've got some links on the DuQIS website, and you can also ask us directly if you'd like.
There's a question about, for me, my involvement in research in quantum about, I'm doing a project about like a quantum, the large title is quantum benchmarking. So it's like we try a way to generate random unitary matrices. Like if we call the unitary matrices are the kind of quantum operation. We use unitary matrices to represent quantum operations, and because the quantity of all the unitary matrices is so large, so there's no way you can have an ensemble of all the unitary matrices and then pick one to do the benchmarking. So we're trying to develop a finite set of ensemble of a pretty good number, like not too large, and to have a pretty good accuracy when you're randomly picking one only from this ensemble to kind of simulate the behavior of entire unitary matrices group. Does it make sense? So what I do in the research is more like a math project, but under a quantum context, quantum setting. And it is really interesting. I really enjoyed it. Cool. Yeah. Well, guys, you can feel free to leave at any time. We'll just wait here. And if you have any question you want to talk with us.
Thank you for
coming.
I will end the recording now.